Now we're good to start. Okay. Hi, everyone. My name is Lian. I'm a computer science and math senior at Wayne, and I'm very interested in quantum computing because it's very cool, and I hope all of you are interested in it as well. Just by a show of hands, who here is like computer science? Okay, so almost everyone. Anyone STEM else? Okay, so this is really introductory. Um, I was gonna go about it in like a more of a mathy way, just because that's the way I prefer, but you'll see that a lot of the slides I'm kind of going to skip at the end because I was trying to prove how like the circuit and how it's being used. But I think I'm going to skip that unless you guys are really interested. And also you'll get the PowerPoint slides afterwards so you can go through them yourself. But yeah, so who here knows anything about quantum computing? Okay, do you want to tell us what you know? Just like anything introductory. Going through it. All right. Yeah, which one is it? Do you know? Because there's one that's like pretty standard in the industry that's Wang or something. Yeah. Okay. Yeah. Yeah. It's a pretty good book. Yeah. Exactly. Yeah. So you probably know more than me. So if you want to interject, go ahead. Yeah. So yeah. So a little about quantum computing. So for the computer science majors here, you already know a computer works in like zeros and ones. But something about quantum computers is that they use quantum bits, which are somewhere in between. So it's basically a linear combinations of zeros and ones. And that unlocks some pretty cool properties such as superposition and entanglement. And we'll talk about those a little more. Um, so who knows the applications of quantum computing, what it can be used for, given that you have like a state that can be between two things or two things at once? Any guesses as to what it can be used for? So the main thing that I will focus on is optimization, but there's so many other applications such as cryptography, drug discovery, and sensing. And if you're interested, maybe we'll do another talk later, delving into maybe cryptography since it's relevant to computer science. But yeah, something about optimization. So quantum computers, so something that classical computers struggles at is there's a lot of problems that we can solve, but because of the computations are so um like their order is exponential, we can't currently solve them with the technology that we have. That's where quantum computing comes in, and it can solve these higher complexity problems like NP-hard problems. And that's just one of the applications that we're going to look into. So as I mentioned before, a qubit is a linear combinations of zeros and ones, and it kind of looks like this. Just you have alpha and beta, which are complex numbers, and you can represent the qubit in this little sphere called a block sphere. And this state is called well, this is the state of superposition. We'll look into that, but yeah. So that's a little bit about a qubit, and it's what you need to start with knowing, so you can kind of understand the rest. Um, Another main thing about quantum computing that is analogous to classical computing are operators. So I'm sure you've heard of the AND gate, OR gate, exclusive OR, and all of these gates. Similar gates exist in quantum computing, although they have different properties and different representations. Some of which are the X gate, which is, or sorry, the Pauli operators. There are four different gates that you probably heard of the I if you've taken linear algebra. It's just the identity, and it's just a 2 by 2 matrix, 1 0 0 1, and it doesn't do anything when you apply it to a qubit. But then you have the X gate, which kind of performs like a NOT gate. So that's what we call a bit flip. If you have a 0, that turns it into 1, and if you have a 1, it turns it into 0. Then you have the Z gate, which is a phase flip, and that just means that if your sign is positive, it turns it into a negative, and vice versa. And then the Y operator, which is a combination of both X and Z. So that is analogous to a rotation around the Y-axis on that block sphere that I showed you previously. And then there's another gate that is pretty important in quantum computing, and that's the H gate. And the H is the Hadamard gate. Now, why is that important? Because it puts the qubit in a state of superposition. So what is superposition? Superposition is a fundamental property which basically puts the quantum computer, or sorry, the state into that simultaneous or sorry, that qubit into that simultaneous state, and it collapses when it measures. So you don't know what the value is until you measure it. And so that's a pretty fundamental property, and this gate is applied almost in every circuit that you'll see. So the other property that I mentioned was entanglement. So what is entanglement? Entanglement is a property where if you know the state of one qubit, you can determine the state of another one, regardless of the distance between them. So, I mean, it's pretty self-explanatory since the word is they're entangled. And how do you make that entanglement? So we saw that the Hadamard gate puts the qubit in a state of superposition. The entanglement happens when you apply a multi-qubit operator. So these are just a few examples. The first example is something you're probably familiar with, the C0 gate, where you have a target qubit and a control qubit. So if the state of the control qubit is 1, then the target qubit flips. And you can apply that flip to 2 qubit or twice, and that will give you the 2 qubit swap. And or you can apply it to a double control. So depending on the state of the first qubit and then the state of the second one, you can determine the state of the third. Another important operator, or yeah, multi-qubit operator, is the Bell state generator. And there's 4 different Bell states, but I just represented one since we won't really be going over them. I think that's less than a little more than just beginner. But those are pretty important, and if you want to look into them, you definitely should. So what's the main purpose of this workshop? There's this algorithm called, or this problem called Deutsch's problem. And given a function of input 0s and 1 and output 0s and 1, you can either determine if that function is constant or balanced. And what does constant or balanced mean? A constant function just means that regardless of the input, the output is always the same. So if you have f of 0, the output is 1, f of 1, the output is 1. So that's a constant function. A balanced function means that the amounts of outputs of 0 is the same as the amount of outputs of 1s. So f of 0 is equal to 1, f of 1 is equal to 0, or like vice versa. And then f of 1 is equal to 0, f of 0 is equal to 1. So yeah, this is a fundamental problem. It's pretty simple classically, but one thing that about it is that classical computers need to query the function twice to determine the result. So you need to compute f of 0, and then you need to compute f of 1 to determine whether they're equal or not. But so this is just like a fundamental algorithm that can show you the use case of quantum computers, although it's not like necessarily useful. It's a fun way to showcase that quantum computers actually work because they need 1 query instead of 2. So you can just find f of 0 and or f of 1, and depending on the output, you know the value of f of 1 or the opposite one that you didn't measure. So yeah, that's kind of what I want to go over. But to do that, there's a lot of steps. First, you need to understand a property of quantum gates. One thing about quantum gates is that they have to be reversible. So here's an example of a reversible and not reversible function that's classical. So this is the NOT gate, or the controlled NOT gate, where as you can see, it's reversible because every output is unique. So you can map it to a specific input. But the AND gate, for example, you have 3 outputs that are 0. So you don't know, like if you're given 0, you're not going to know if the input was 0, 0, 0, 1 or 1, 0. And you need to know, or sorry, the function needs to be reversible in quantum computing because if it's not, then the system loses a lot of information and it collapses, and then you're not in a quantum state anymore. And it's kind of like useless at this point. Okay, so how do we make a classical gate reversible? Does anyone have a guess? Okay, I'll just say it. And this is classical, by the way. This is a classical way of turning a gate, like the AND gate, into a reversible gate. And the way to do that is to apply a third gate, and then the result of the AND operation, C0 it with that third bit. So here you have A and B, and then you apply that third C, and then your output includes those inputs, so A and B, and then the result of C exclusive NOT F of A and B. So as you can see here, in this case, when you read A, B, and then the result, each output is different and can be mapped to a specific input. And so that's what you need to do for quantum gates. So why am I yapping about all that? This function is classical. So if you wanted to kind of like turn it into a quantum gate, which is what we call a quantum oracle, um, then these are like the functions that are reversible. And so yeah, so at this stage, all you need to do is like, okay, so this is a quantum oracle that is basically what I just showed you, but applied to qubits instead of just regular bits. And if you set y in this case, so these are your two qubits, you set y to be 0, then and apply the oracle, you're just left with this result, which is an x qubit and the f of x. And if you apply, and then at this stage, all you need to do is find f of x to get your result. And this is important because it introduces the concept of a phase oracle, which is a specific type of oracle, but instead of applying the function to the second qubit or the 0 to the second qubit, you're you introduce a phase, which means like positive or negative. And that's pretty fundamental when it comes to developing the circuit of sorry, forgot his name. Deutsch's algorithm. So yeah, that's like the main part of Deutsch's algorithm. It's the phase oracle. And if you guys are interested in math, there's a pretty simple proof that you can do, but I won't go over it because not everybody's into math. So this is what the quantum gate looks like, or sorry, what the circuit looks like for Deutsch's algorithm. You know what an X gate does now? It's the bit flips. So if you have a 0, it turns it into a 1. You know what a Hadamard gate is? It puts the qubit in a state of superposition. You know what an oracle is, which is, in this case, a phase oracle. And this is the Hadamard gate again. And this is the measurement operator. So it does exactly that. It just measures so you can get your result. And as you can see here, you have psi of 0, psi of 1, 2, and 3, and 4. And I just put those so you can like see the state in different, or sorry, yeah, the state of your system at different points in time. So before, it's just 0, 0, because your qubits start with 0, 0. And then you apply the NOT gate to the second qubit, so it makes it 0, 1. And then all right, guys, you're going to hate me for this. So I don't know if I'm going to go over this, because this might be a bit too mathy. Because I'll just give you a sneak peek. I'm basically going over how we went from this to finding the result of the function to see if it's constant or not. And I don't know if that's what you guys want to do. Do we want to do the math stuff? We want to do the math stuff? All right. No one gets to complain though, so. All right, so we're at psi 2. So psi 2 applies the Hadamard gate, which just means that now both qubits are in a state of superposition. And the Hadamard gate, you can either write it as plus or minus because it's simplified, or you can expand it into what it actually looks like. So for the plus, it's 1 over root 2, 0 plus 1. The minus is 1 over 2, 0 minus 1, but in this case, I just kept the minus. So after that, you go through the oracle. What the oracle does is you can apply it to either the entire thing or you can distribute it to each qubit. And we already know what that oracle is since I showed it. I didn't prove it though. But yeah, you apply that oracle and then, yeah, so we're at psi 3. What are we doing here? We're applying 0. So remember the whole point of this was to read f of 0 or f of 1 to determine if the function is constant or balanced. So in this case, we just chose randomly to, compute f of 0 and kind of read the result. So, factor out the minus. Okay, yeah, so I kind of wish I had both of these on the same slide. So you see that minus qubit here? We're going to factor that out. And we technically don't need it here, so like mathematically it doesn't change anything, so we can just disregard it. And at this state, if you can read this, because it's hard at first glance, you have two possibilities. Either f of 0 is equal to f of 1, or f of 0 is not equal to f of 1. And that's basically the difference between doing it with a quantum computer or doing it classically. Like you wouldn't have this situation if you were doing it classically. So if f of 0 is equal to f of 1, then it simplifies to, all right, then, okay. So in each case, there are two cases. If f of 0 is equal to f of 1, then that can either be equal to 0 or it can be equal to 1. And these are the two cases here. And so if they're equal to 0, then what happens? Then this turns into 0. So that just results in a 1. And so we're just left with 0 plus 1, 0 plus 1. In the case where it's equal to 1, then you're left with that's the whole point of the phase. You're left with a negative sign here. So it's minus 0, minus 1. And then simplify that or like merge that into one formula, you get plus or minus 1 over root 2, 0 plus 1. You can do the same thing for the not equal. I won't go over it. All right. So now that we went through psi 3, what do we have to do? We have to apply the Hadamard gate again. So that states as plus or minus. Right. So where we were here, sorry. These are basically represented, I don't know if you saw before, but we had the minus qubit, which we said we can rewrite as 1 over root 2, 0 minus 1, or the positive qubit that you can write as 1 over root 2, 0 plus 1. So in this case, this is the positive qubit and this is the negative qubit. So just to simplify it, this is either plus or minus positive qubit, plus or minus negative qubit. And then we apply the Hadamard gate again. So what the Hadamard gate did on the first run, if you remember here, is it turned the 0 into a plus or a minus. So when you apply it again, it basically reverts the changes, because what did we say about quantum gates? They're reversible. So you apply the Hadamard gate to the plus and minus, and you get 0 and 1. And so, all right, so these are your results, and that's basically your answer. Because if we measure 0, then the function is constant. And if we measure 1, then the function is balanced, because the results are different. And all right, it's gonna end here, but it's not ending yet, don't worry. Because now we're gonna actually code it up with Python. And these are just some sources. I use this video a lot if you want to kind of go through the proof again. And there's the proof for showing that, what was that little exercise I gave? Yeah, that proof is also included in the video. I don't know, I really like the video. But yeah. All right, who has their laptops and who wants to do some coding? So